First of all, thank you for this invitation. It's a pleasure and honor for me to be here and to have the chance to talk about this new and fast-growing discipline that is electromagnetic signal and information theory. What we try to do in this discipline? I think that we do something like what is doing this killer wave that you can see on the screen. And I like thinking that this killer wave wants to see the world from a different point of view. And in some way, electromagnetic signal and information theory does something like this. It starts from some very established disciplines, for example, electromagnetic theory, information theory, and so on, and try to look at this discipline from a slightly different point of view, trying to blending them. In some way, it's like to take different metals and to use this metal to obtain a different alloy. And our hope is that this alloy is stronger, it's let us say better, is something different from the disciplines we start. And electromagnetic signal information theory is a part of a quite huge and important field of research that is the analysis and the study of the relationships between physics and information. And this started with Maxwell, that in the theory of heat, imagine the presence of a demon that is able to open a door in a box. And this box is divided into two different, let us say, sub-boxes. And there is a gas. And opening this door, the demon is able to force the molecules that are faster on the right and the molecules that are slower on the left of this box. And this violates the second thermodynamic law. So there is a large research on this. Many very important researchers worked on this problem. But what is really interesting is that this is the first example of relationship between information and physics. The demon is able to use information on the particles to obtain something that is, let us say, particularly interesting, the violation of a thermodynamic law. And I was a bit puzzled about this, and I tried to understand the relationship between physics and information in my field of research, that is wireless communication, in particular, of course, the electromagnetic part. And if we look at a communication system model, this is the OSI standard model, well, the information is everywhere in the layers. But let us focus in particular on the physical layer. In the physical layer, information is something quite abstract, is basically measured in bits. And this is the kingdom, of course, of Shannon. And in the last years, there is a great interest toward the application of this theory to space communication systems. And in MIMO communication systems, the model that is used is basically based on the channel matrix. We have a transmitter, a receiver, a string of bits in input and output, and all this is modeled through a matrix, channel matrix. And by applying the singular value decomposition, it's possible to obtain a model in which we have many spatial communication channels. Each of them is able to transmit bits. And what is a quantity that is important is the maximum number of these parallel subchannels. And this number is called the effective number of degrees of freedom of MIMO systems. And if we consider the matrix H and we evaluate the singular value decomposition, we have this behavior of the singular values. We must consider, of course, the presence of noise. And so this means that if we have some noise level, we have to consider only the singular values above the noise. And the number of singular values basically fixes the effective number of degrees of freedom of this communication system. This is the Shannon approach that allows to evaluate to evaluate the capacity. This is the capacity per channel use for a high signal noise ratio. As we can see, we have a limitation that is given by the effective number of degrees of freedom. And of course, we have also the noise level, in noise power in this part. And well, this is the Shannon approach. But we want to, in some way, extend this approach to a more physical model. And the simplest model is a current that radiates, that models the transmitted part. And this field is observed on an observation curve. The relationship between the field on the observation curve and the current on the antenna is given by this integral that is the radiation integral. And this is the integral on the domain D, where there are the sources of the transmitter. This is a simple model, but let us say, it catches the most important characteristics of the transmission in the space, in the free space. And if we consider this model, well, we can go, let us say, a bit more down compared to the concept of bit, because now we are at a physical level. And so let us come back to the OSI model. In order to analyze this physical system, we need to arrive at the Maxwell equation. We have to talk about the electromagnetic fields, waves, and so on. And all these concepts are embedded inside the physical layer, but it's quite, let us say, hidden inside the physical layer. So it's interesting to expand this layer and to introduce another layer that we will call the deep physical layer. In this layer, we have fields, we have electromagnetic fields, we have Maxwell equation. So this is the kingdom of Maxwell. And what we have is to understand the relationship between information at this level and information at this level. Information at this level is an abstract concept. It's information, it's a mathematical approach to information. Information at this level is instead something real, is related to the field configurations. And so it's the kingdom of Maxwell. And so we have two levels. In the physical layer, we have abstract bits. But in the deep physical layer, we have something more real. And so the question is how to define information at this level. And to define information in a, let us say, more physical way, it's useful to recall some very basic, very simple concept regarding information. Let us consider a system. It could be a physical system on which we have some uncertainty. For example, we have an uncertainty about the state of the system. We perform some measurements, and so from this a priori uncertainty, we obtain some more precise information about the state of the system. So we have some a priori uncertainty. Information is based on the decrease of uncertainty from a priori to a posteriori. And this practically shows that the core of any mathematical theory of information is the proper mathematical definition of uncertainty. And it can be based on probability, for example, the Shannon theory, that is surely the most important, most successful information theory, but there are some other information theory, and one of these is the Kolmogorov information theory, and I will talk about this in a few minutes. And so let us come back to some basic concepts on information. And let us suppose that that Romeo wants to meet his Juliet. He take a box, it can be a box of chocolate, and divide the box in a number of subspace, in this case 36. And each of these square is associated to a different information. For example, he take the chocolate and he puts the chocolate in the position B3. And position B3 means that they will meet behind the church. And he asked a friend to bring this box to Juliet, but unfortunately, during the travel, the chocolate moves. And so the information that arrives is erroneous. So, for example, it means that they will meet in the garden. And this means that in this case, this transmission system does not work. How to solve this? Well, Romeo can analyze what happens when this box moves. And for example, it finds that, yes, this chocolate can move, but doesn't go outside this circle. So he identifies a circle of uncertainty, or more general, a sphere of uncertainty. And based on this sphere, he divides this square, this box, into, in this case, only nine different pieces. And in this case, it transmits less information, but he's sure that in spite of the travel, the information arrives in the proper way. And so, basically, this means that the amount of information that can be transmitted is related to this is just a sphere-packing problem. How many spheres we can pack inside this chocolate box? And of course, the number depends on the radius of these spheres, that means the uncertainty, and also on this box. This is a box that has 2 dimensions, but let us suppose that the box has 3 dimensions. Clearly, you can put much more, a much larger number of spheres. And if this box has 4, 5, 1,000 dimensions, you can put a very large number of spheres. And the amount of information that we can send is just the number of the sphere of uncertainties that we can pack inside this box, measured in bits. And so let us come back to our problem. And in this case, we just have to change the chocolates with the field configurations on the observation curve. And a simple way to identify the amount of information that we can have on the observation curve is to count the number of distinguishable field configurations that we can obtain on omega. So the problem is quite simple. How many distinguishable field configurations we obtain on the observation curve? And to solve this, we need to, this is, of course, the number of the amount of information is just log of 2 of this number. And so to solve this, we have to characterize in some way the set of all the fields on the observation curve. And a quantity that is useful is the concept of the number of degrees of freedom of the field, introduced by Bucci and Franceschetti in 1988. This is definition. It's quite mathematical. I do not enter into the definition, but I want to give you the general idea. And let us suppose that we have a set. In our case, is the set of all the field configurations on the observation curve, but in general, it can be any set. This is a set in a 3-dimensional space. And I want to approximate this set with a linear subspace. So I start trying a linear subspace with 1 dimension, a line, and I evaluate the maximum distance between the set and this linear subspace. And then I try to change this linear subspace, and for example, in this case, I obtain the smallest maximum distance between the set and this subspace. Then let us suppose that I can accept an error that is not larger than epsilon. And so I can check if this distance is smaller than epsilon. If it's smaller than epsilon, this means that I can substitute all this set with this line, because the error is smaller than the error that I can accept. But in this case, let us suppose that it's not the case. So what can I do? I can improve things. I can try, instead of a line, a plane. That means that in this case, I have a two-dimensional linear subspace. And again, I can try different two-dimensional subspaces until this distance between the 2D subspace and the set is small, is the smallest one. And then I try again to check if this distance is smaller than epsilon. And if this is true, I can substitute all this set of points with this linear subspace. And in this case, I must use a two-dimensional subspace. And so I can say that the number of degrees of freedom of this field, this set E, is equal to 2. Just because with a two-dimensional subspace, I can approximate all the set. And this is basically the concept of number of degrees of freedom. So let us come back to our electromagnetic problem. And we have the currents, we have the field. This is the radiation operator. It's an integral operator. We suppose that we work in Hilbert spaces with L2 standard norm. And we suppose also that the current is a bounded set. This means that the norm of the current is limited. And this is quite acceptable because it means that the energy of the currents is limited. And then I can take this integral operator and I can diagonalize it. This means that I can find a basis Bk for the current and a basis Uk for the field, such that the coefficients of the field and the coefficients of the currents are related by a very simple relationship that is reported here. Sigma k is a real number, and it's called the singular values of the radiation operator. This is the kth singular value. And it tends to 0 when k tends to infinity. And this has a very simple and clear representation in functional spaces. Let us suppose that I have a current. I can represent this as a functional point in an infinite dimensional space. We can imagine that the components of this point are just xk. And again, if I have a field E, I can represent the field as a functional point in a set Y that is the set of all the fields on the observation curve. And in this representation, the radiation operator just maps the points in X to points in Y. And now we can analyze what happens when we consider the singular values. This is our representation. This is the current. This is the field. Of course, we work in an infinite dimensional space, so we have an infinite dimensional basis function. But what happens is that the singular value has an E, and basically this means that if I fix an approximation epsilon, I can apply the concept of the number of degrees of freedom, and I can substitute all this set, and this is the set of all the fields on the observation curve, with a linear subspace, basically. And this linear subspace must have a number of dimensions that must be equal to the number of degrees of the number of singular values above epsilon plus 1. This is the dimension of the linear subspace that I need to consider if I want to approximate any element of the set A, of the set E. And this means that this infinite becomes NDF epsilon. And this allows to approximate the field with an error smaller than epsilon. And this is a very powerful theory. But the problem is that we are investigating a different problem, and in some way an opposite problem. In fact, what we want is that these points, and each of these points represents the field configurations on the observation curve. These points are at distance not smaller than 2 epsilon. In practice, we need a 2 epsilon sphere packing. And the maximum number of sphere of uncertainty that we can pack inside this this set Y is called the Kolmogorov 2 epsilon capacity. It's the logarithm of the number. Instead, in approximation theory, we want the opposite. In practice, we want that there are no area volume of the set Y that is not covered by a sphere, because we want to approximate all the elements of the set. This is a problem of epsilon sphere covering, and the minimum number of sphere that allows to cover this set is called Kolmogorov epsilon entropy. But unfortunately, this does not work, because in this case, we are not able to clearly distinguish different configurations. And so, in practice, we have two problems. In transmission, information transmission, we are interested in an epsilon packing, but in approximation theory, we are interested in epsilon covering. What is the relationship between these? And in practice, the 2 epsilon Kolmogorov capacity is not greater than the Kolmogorov epsilon entropy. That means in practice that the number of balls that I can put in this packing problem is smaller than the number of balls that I can put in this covering problem. And in practice, this means that the number of degrees of freedom of Bucci is an upper bound for the number of dimensions of the 2 epsilon packing. And this is a first relationship between a communication system, a communication problem, and an approximation problem. But in reality, we are interested in Shannon theory. In this case, I worked with Kolmogorov information theory. What is the difference? In practice, in Kolmogorov information theory, we have sphere of uncertainties that are hard. I'm sure that the noise is such that the signal plus noise does not go inside a different sphere of uncertainty, is always in this sphere of uncertainty. Instead, in Shannon, we have, let us say, a soft sphere of uncertainty. In any case, there is a probability, even if very, very small, that the signal goes in another, also the electromagnetic field configurations that we measure in presence of noise, goes in a different sphere of uncertainty. However, if we apply the law of large number, we discover that this soft sphere of uncertainties tends to become hard sphere of uncertainty when the dimension of the space tends to infinite. Just to understand, when the number of dimensions of the chocolate box of Romeo tends to infinite, so he has a chocolate box of 1,000 dimensions, this sphere of uncertainty of Shannon tends to become hard. And so we can compare these two information theory, supposing that the sphere of uncertainty of Shannon is hard, and what we have is this. This is the model using the integral operator. So the Kolmogorov approach, in this case, we use the Kolmogorov approach in this case, and the 2 epsilon capacity of Kolmogorov is given by this formula. This is the number of degrees of freedom of the communication problem, and we know that the number of degrees of freedom defined in approximation theory is an upper bound for number of degrees of freedom in case of communication problem. If we consider the Shannon theory, we have this model, and this is the effective number of degrees of freedom that I introduced before. And what is interesting is that the physical problem is the same. This means that when we consider the singular value decomposition of this matrix, we have practically almost the same singular values. And in this case, this is the NENDF that is very close to NDFC. And since the number of degrees of freedom of epsilon is an upper bound for this, it will be also an upper bound for this. And this means basically that the number of degrees of freedom of the field is an upper bound for the number of MIMO spatial channels that can convey information reliably. This means basically that this quantity, that is an electromagnetic quantity, is defined in a pure electromagnetic way, is a limitation for something that is defined in a pure communication, let us say, theory, the number of MIMO spatial channels. And it is an example of how the physical limitation limits the amount of information that we can obtain in communication systems. And let us consider some simple examples. This is a circular source that has radius A, and we observe the field radiated by this source on a circular observation curve. Beta is the free space wave number. And the singular values, the M singular values, normalized on the first one, is given by this formula. It's a product of two functions, but when this observation curve is far from the source, we have that this function tends to 1, Fm, and so everything simplifies in this way. And this is the relationship between the coefficients of the field, kth coefficients of the field expansion, the kth coefficient of the current expansion, the singular values, and this is the noise. This is just to recall this formula that we have found before. Now, let us consider the singular values in some specific cases. And this is the plot of the singular value considering different radius of the source. And we can see that, yes, there is a transition window that becomes narrower and narrower when the radius increases. But what is interesting is that in any case, we have a knee of the singular values. And this knee is basically limits the number of degrees of freedom to 2 beta A. Beta is this, A is the radius of the source. Basically, what happens is that in this area, where we have high singular values, let us look at this formula, yk, sigma k, xk, nk. Let us suppose that the k is inside this area, for example, is this, and xk is 1. In this case, sigma k, if it's in this area, it's high, it's close to 1. And so yk is also high. This means that yk is much higher than nk, and is not buried by inside the noise. We can retrieve this information. But let us suppose that we consider the field associated to, for example, these singular values, where we have minus 50 dB. In this case, if, for example, xk is 1, sigma k is 0.00001, this means that yk is very, very small. And so it's buried inside the noise. It's impossible to identify yk because it's covered by the noise that, for example, is 0.01, and so it's much higher than this quantity. So we are not able to retrieve information. And this is the meaning of the singular value decomposition and the number of degrees of freedom in terms of information. We are not able to retrieve information associated to singular values that are very low. And since the singular values becomes very low after this point, we know that only the first 2 beta A are important. At the end, the maximum number of spatial communication channels that we can obtain with this communication system is equal to 2 beta A and is limited by the number of degrees of freedom. And let us consider another interesting thing is that if we consider this formula, we have that the number of degrees of freedom is equal to the length of this circle normalized to lambda over 2. And this is a quite interesting and powerful result because it shows that information is limited on the surface of the radiating system. It depends just on the surface. And this is, of course, related to the uniqueness theorem, and it's another example of how physics limits the amount of information that we can transmit. And this is another example. We have a linear source. We observe the far field in the angle theta, observation angle theta, and the far field is equal, apart from this formula, is given by this, is proportional by this function fky. Ky is equal to beta sine theta. Theta is the observation angle. And f is just the Fourier transform of the field on the aperture. And note that the aperture is limited. So it's an integral from minus a and a. And if we come back to Shannon theory in time domain, this is basically a Fourier transform, of course, and it is a Fourier transform of a band-limited function. Omega is the angular bandwidth. And we know that this function can be expanded using the Shannon sampling series, so sinc functions. And what we have is that the number of samples that we have, considering a bandwidth omega, an angular bandwidth omega, and an observation time t observed, is equal to omega t over pi. This is the number of samples that we have in this observation time, and is called the number of degrees of freedom of the band-limited function. So this is exactly similar to this, and we can apply this theory. This means that we can consider this as a band-limited function, but in this case is a spatial band-limited function, not time band-limited function. And the number of degrees of freedom that we have, that means the number of samples, is equal to the bandwidth, 2a, and the observation domain. What is the observation domain? Clearly, in this case, sin theta changed from -1 to 1. So the observation domain is limited between minus beta and beta. It's an angular, let us say, observation domain. And we can do some calculation, simple calculation. And this means that the number of degrees of freedom is equal to the length of the observation of the source normalized to lambda over 2. That is exactly the same formula that we have obtained before. Again, the number of degrees of freedom, and so the number of spatial subchannels in MIMO communication systems, is limited by the electric length of the source. And why there is this limitation? There is something, let us say, intriguing. Let us consider this function f, and this is an analytic function. This means that it has an infinite number of samples. Some samples falls inside this range, minus beta, beta, but there are an infinite number of samples that fall outside this range. And what happens to these values? Why we do not consider them? And there is an interesting relationship between information and energy. To clarify this, let us consider that when we observe the field along theta, basically what we do is to extract a plane wave from this plane wave spectrum. And the plane wave is such that the direction of the plane wave is along the observation domain. Any plane wave, in this case, this is a two-dimensional case, has a ky and kz. And of course, ky square plus kz square must be beta square. And so we have two possibilities. The first one is that ky is smaller than beta. And this means that kz is real. And so we have traveling wave. But the other possibility is that we consider a ky that is outside minus beta beta. In this case, we have that kz is imaginary, and we have a evanescent wave. These waves are associated to not active, but reactive energy. And these are not considered when we count the number of degrees of freedom. The number of degrees of freedom, in this case, are related only to solutions that are associated to active energy, not reactive energy. And this is an example of relationship between information and energy. There is, in some way, another interesting result. It's an asymmetry between space and time in communication system that derives from this formula. Just to understand, in a Shannon theory, we can increase the number of degrees of freedom as we will by increasing the observation time. In this case, in space communication system, this is not possible. The number of degrees of freedom is related to the length of the antenna. We cannot increase the, let us say, observation domain. And this is due to the fact that the observation domain is forced to be between minus beta and beta. And this means that the only way to increase the number of degrees of freedom in a space domain is to use larger antennas. And this is why MIMO, very large MIMO, massive MIMO antennas are so interesting in communication systems. Just to give another example, this is a square radiating surface. In this case, we have Kx, Ky, and Kz. We can evaluate the number of degrees of freedom in the same way, because in this case, the far field is a band-limited function, and the number of degrees of freedom is equal to basically 12, the number of samples on the square between minus beta and beta along Ky and Kx. But we have to remember that we can cut all the waves that are related to energy that is not active, to reactive energy. And these waves are in these parts. So what happens is that we can restrict the number of degrees of freedom only to this circle that is called the visible circle. And the number of degrees of freedom turns out to be pi multiplied the area of this surface over lambda square. And this is true for each polarization. That means that for two polarization, the number of degrees of freedom is 2 pi AT over lambda square. And this is also the maximum number of MIMO subchannels that we can obtain to transmit information using space-time communication systems. What is interesting is that if we consider the gain is equal to 4 pi multiplied by the effective area of the antenna over lambda square. And we can note a similarity between this formula and this formula. And this is really interesting. Indeed, there are some connections about what we can obtain in gain and what we can obtain in terms of a number of parallel subchannels. Of course, also for the gain, we can obtain very, very high gain, the super directive antennas and so on the directivity, not on the gain, to tell the truth. But what is interesting is that when we try to obtain directivity that is much larger than this, we have a lot of problems. And it's the same physics that limits the directivity, the gain, and the number of spatial subchannels in communication systems. Is the physics, is the Maxwell equation that play the rules. And we try to apply these ideas. We did a lot of research. For example, we increased the channel capacity using scattering elements, and these are photos of almost 20 years ago. This was the PhD thesis of Daniele Pinchera, that now is one of my colleagues. And among this research, we also built a device that was, I think, was quite interesting. It was called Adam, and basically it consists in a MIMO antenna and many scattering elements that are placed around the antenna. And we control these devices using pin diodes. It's a 6-bit control in practice. And we optimize the scattering properties in order to increase the channel capacity. And these are some results obtained with our colleagues by university, Jensen and the colleagues. And this is what happens when we do not have these, let us say, controlled environment around the antenna. And these are frequency space, singular values. And these are singular values for the first spatial channel, changing the frequency. And these are the singular values of the second spatial channels, and these are all the frequencies. And when we used this device, we had this result. This means that if the signal-noise ratio is, for example, 15 dB, we have that this system is able to double the number of available channels. And this means a significant increase in the channel capacity. And this is a device that we built and published in 2006. Now there is a very high interest toward this kind of solutions. Of course, now there are some ideas, some technical solutions that are much more sophisticated, but this was just the basis, let us say, the starting point. And so just another example to give an idea of what we can obtain. This is the University of Cassino. Let us suppose that we have an antenna having 11 transmitters. And we put some scattering objects in order to obtain a scattering toward this position. And the idea is to maximize the channel capacity in this communication. And what we do is to consider an antenna. These are 7 elements receiving antenna, to consider the electromagnetic field that impinges here. And we evaluate the epsilon covering. From the epsilon covering, we evaluate all the distinguishable field configurations that we can identify using these 7 elements. And this is the maximum amount of information that we can transmit from this point to this other point. Basically, we used the theory that I showed before. And this is an example in which the same message is transmitted using the 6 bits that is used in LTA, 8 bits that is used in 5G. If I remember, 10 bits for Wi-Fi 11, and then the solution when we consider the sphere-packing that I showed before. And this is what happens in using 6 bits and 8 bits. This is Wi-Fi 11, and this is the solution using sphere-packing that gives the maximum number of distinguishable field configurations and the maximum number of transmitted information. And so, this is the end of a long journey, and I'm particularly happy to have been invited in this conference because for the first time I showed my idea on horse and horseman. In my opinion, horsemen is communication people. They must preserve information. Their work is fundamental. It's a great work. And the horse is the electromagnetic people in some way, the electromagnetic theory that must bring in some way the message. And horse and horsemen must work together. Horse need horsemen, and horsemen need horse. And so it's important that they work together. There is this idea of electromagnetic signal and information theory in which people from communication and from electromagnetic theory are working together. And this horse and horseman is beginning a very, very powerful field of research or on my idea. And there are a lot of people that are working together. There is a communication society initiative that is electromagnetic signal and information theory that is centered, focused on this idea. And there is a large community that is working now. And so my hope is that this presentation will raise the interest of students, of young researcher or PhD toward this new and fast-growing discipline. I understand that it's not so easy. Working on this means that you must, let us say, lose let us say, safe zone, because you must work on different tables, electromagnetic field, information theory, and so on. But my idea is that it's worth exploring the deep physical layer. And because in deep physical layer, on my idea, there is plenty of room, and it's really interesting to investigate this new world. So thank you for your attention, and of course, Merry Christmas. Thank you.
Okay, Professor Migliori, that was a great talk. I really want to thank you a lot. I remember your first presentation here in Brasilia. That was great work. You keep going on the great work. So thanks a lot for taking the time to give us a short talk about all the work you did since that time.